Welcome back, everybody. I hope you can hear me well. Does this sound okay in the audience? Great. So I just wanted to give you some quick messages first, and then I'm going to try to wrap up what we did on Monday, and then we're going to have a summary and discuss the final project. And then for those of you who wish to hang around till 5, feel free to do so. If you have other plans, I mean, yeah, just follow your other plans. So just a quick reminder of some practicalities. Today we are going to wrap up what I didn't finish on Monday, and then we take a quick summary and use the rest of the time to discuss the final project, which is more or less of the same type of length as the midterms. It's perhaps a little bit easier than the last one. So writing a code for the solar system is normally a big challenge, but I'm very proud of what you guys have done. I mean, there's so many fantastic second midterms. So it's been really a great pleasure to read them. And I think I've gone through half of them. So I still have half of the midterms to grade, but overall, it's just a fantastic job you people have done. Congratulations to you all. Now, the plans for Friday is then, for those of you who wish to come in here, we can just work on the exam project. And similarly, next week, if this is something which fits your plans, you can just swing by here. And if you wish to discuss the final one, feel free to do so. We may, depending on your mood and where you are, we may skip Friday next week, or we can still have a session. That depends very much upon you. But at least Monday and Wednesday, we will be here. So let me try to wrap up what we did on Monday. And this was a system with the Lagrangians and couple springs. So we were looking at the Lagrangian. I'm going to use the slides, if that's okay with you. And you can actually look this up a little bit later if you want to as well. Everything is in the slides here. The Lagrangian, which we started with, so this was a system of 3 coupled objects, and we put one of them to have twice the mass of the other ones, and this could be a model for the linear carbon dioxide molecule. And many of these kind of molecules and solids and so on, they can actually be modeled as atoms, classically model atoms, which just vibrate around their equilibrium position. So this is a model which is very much favored in a field which is called molecular dynamics. And molecular dynamics is actually used solving Newtonian type of problems. It could be with something like a simple force like the harmonic oscillator. So you just have some springs which couple the different atoms. And then when you heat up the system, these atoms will vibrate more and more. And so this is a typical model which is used in material science. You can be more refined and you can set up a potential like this Lennard-Jones potential, which we have seen in different exercises, and use that one to model the interaction between the different atoms. In essence, what you've done is to freeze out all quantum mechanics and you treat the system as a classical system. And that is the typical way you would deal with the large systems where you have too many degrees of freedom, so that you cannot deal with a quantum mechanical, you cannot use a quantum mechanical approach because you have too many degrees of freedom. So if you have an atom with hundreds of electrons, what you essentially do is that you freeze out all of the quantum mechanics and treat this as one object, one point particle. So what we did was to start with the Lagrangian, and then we used this famous Euler-Lagrange equations and found the equation of motion, where we now have a spring constant K, we have a plane harmonic oscillator, this L would be the relaxed lengths of these springs. Normally you would put that one to L equal to 0 for simplicity. And then this X1, X2, and X3 are the equilibrium positions. And what we did was actually to change. So when you look at these equations, these are coupled equations. What you can do is actually to change. So this is one of these cases where you have 3 coupled differential equations, which you can then change into 2, which can be solved analytically by a smart change of variables. So you could choose the central mass motion, and then you define coordinates Q1 and Q3. And that allows you to redefine the potential energy in terms of just this Q1 and Q3. And this is roughly where we ended on Monday, we can then make a transformation for X1, X2, and X3 in terms of the new coordinates. And if we do this, we get something which doesn't look that simpler as the previous one. But when we now set up the equations using Euler-Lagrange equations, this actually simplifies to a Lagrangian, which now has the velocities of Q1 and Q3, and the velocity of the center of mass squared. So this is the kinetic energy of the central mass. And then we have this additional term here. And then we have the potential energy from the standard harmonic oscillator potential. And then we get 3 equations of motions, where the acceleration for the central mass, as you have seen before when we did the solar system or the two-body system, in the two-body system in particular, the central mass acceleration was put to 0. So that means that the central mass moves with a constant velocity. And in this particular case, what we get are actually 2 coupled differential equations instead of 3 coupled differential equations. So by this small trick, we have been able to change from 3 coupled differential equations to 2 coupled differential equations. And this is something which then can be solved analytically if we now remember that for harmonic oscillations, we have something which goes like a cosine and sine. In this case, there is no damping term, which means that the solution most likely can be parameterized in terms of cosines and sines, which in turn means that we can actually rewrite this as an exponential. So you can actually try a guess solution. And the typical way of doing that now, because this equation, the last one, is trivial, that is the central mass motion. So the central mass velocity is just a constant. So what you could do now, you could simply guess that there are 2 types of solutions. There is a driving frequency. And since we are going to look at the ratios here, you can then simply solve for the ratio, and you can put one of these to 1, and that just scales the other variable. And when you plug that in, you get an equation in terms of these ratios, and you divide away e to the I omega t, so you can get rid of that one. And you just divide it out because that appears in all the equations. When you plug it in, you just plug in that ansatz for the solution in here for Q1 second derivative, Q3 second derivative, and then divide out e to the I omega t. And then you have these 2 equations here, which you then can rewrite in terms of A and B. And when you do that, you get an equation which you can actually solve if you identify omega squared, which is the unknown quantity in terms of an x squared. So then you would have x in here, and these are just constants, omega 0, which is defined in the standard way by the spring constant divided by the masses. This is also one reason why we put all the masses to be the same. And when you solve this equation, which turns into a second order equation, you can actually find a solution where omega is equal to omega 0, and that gives you A equal to minus B, or the other solution, which says that omega is equal to omega 0 times square root of 2. And then you have A equal to B, and if you scale B equal to 1, then you have only one unknown coefficient. So this is an example of how you can set up such equations. Now, in the slides here, you will find more complicated systems. There's an example of the double pendulum, but we will not cover that because this is actually our last, how to say, formal lecture, because on Friday we are going to actually look at the solution of the final. We will also do that today, so we have some more time to discuss that. But you can take a look at the slides here and look at the more advanced examples where, for those of you who have taken a course in linear algebra, these are cases which you can actually rephrase in terms of coupled linear algebra equations, which then can be solved by standard linear algebra methods. And that's typically the way you would do that in this type of harmonic oscillation problems, as we discussed on Monday for the case of an earthquake model. So I'm going to leave much of the things which are here as something you can dive into if you have the time and an interest. Taylor's chapter 9, I think, or 10 on vibrational modes is actually a very interesting read for those of you who wish to see how you can use linear algebra on these coupled harmonic oscillation problems. And there is this double pendulum is a very exciting problem, but we won't have time to cover it. So I'm just going to leave these things for you to take a look at. In case you want to, there's lots of more material which we won't have the time to cover. Conservation laws is actually something we have discussed 2 weeks ago. So this contains just the material which we covered earlier. So the thing which I wanted to bring up more now is a discussion of what we have done this semester and what we can expect from the midterm here. So I actually love this image here. This reminds me of the standard exam period. So I don't know if you've seen this. As I told you, when I went to university, we used to have these exams which were just torture. You would have a course like mechanics, which would span over 2 semesters, and the exam could often be from 5 to 7 hours. And if you had a bad day, you had a bad day. So I always felt like that 1 week before the exam. And then when the exam was getting closer and closer, then you had this feeling that you having procrastinated for so many days meant that you were getting closer kind of crisis. And then after the exam, you just forgotten everything. So I hope that by the way we have been running this course with projects where you have been able to collaborate. And one of the things which I really like to see when I read the midterm answers is to see how many of you actually collaborated, because one benefits a lot. And the hope is obviously that instead of you simply have to regurgitate whatever you've done, that actually something sticks of what we've gone through the semester. That's my hope. Now, you've probably seen this, been through this kind of case where when you shift to the next semester, the teachers would say, you've seen this before. Well, never seen this before. So hopefully when you now see Newton's equations of motion, and since you've been solving these equations again and again, and you're going to do the same thing in the final, that at least some of these things actually stick. Actually, perhaps not remembering all the types of equations, but rather the way you solve the equations and the kind of insights which you've gotten from solving the equations. I think that's the most important thing. Yeah, I'm going to skip that one. Well, I obviously hope this is not the case. And that rather, let me see if I can increase it. Yeah, I hope you can see that. You can also see up, you can also look at the slides later. So what have we done this year? So we have focused on understanding the equations of motions based on the forces. We've been looking at forces, how to decompose a system. We've looked at conservation laws based on the type of forces. So if you now know that the curl of the force is equal to 0 and the force depends only on the spatial degrees of freedom, then this is a clear indication that most likely this is an energy conserving force. If you have a force which depends only on the relative distance between the particles and you only have internal forces, then most likely angular momentum and linear momentum are conserved. So these are important features of the forces, and you've seen it again and again with the gravitational force. You saw this with this kind of Lennard-Jones potential model and many, many other potential models. And remember now that if your force, which is given by the derivative of the linear momentum, is not a constant, then clearly, or is not 0, that clearly means that the linear momentum is not a conserved quantity. We've been looking at various types of motion. We've been analyzing energy diagrams. So the first midterm, we were looking at the energy diagrams, the potentials, and then from that, we could say something about the type of motion which we can expect. You saw that in the second midterm and in many, many other cases where we've been plotting the potential. And from that, we can say something about what kind of motion we can expect. So I hope that having gone through all these examples, because many of you will do quantum mechanics and do electromagnetism, and then you will meet this type of way of analyzing a problem. If you plot the potential, you can actually say a lot about what kind of motion you may expect. Then we looked at small oscillations. So the harmonic oscillator is something which you will meet again and again. So when you're looking at molecules, for instance, in quantum physics, then the lowest lying states in a molecule, the energies, they can actually be approximated with vibrations around a minimum. And many of these states can actually be identified as harmonic oscillator oscillations. Then we've been looking at transformations of variables, and the two-body problem is one of these classical problems where you can actually solve things analytically. We've been looking at central forces and two-body problems, and the second midterm was actually you practicing this. And hopefully, by being able to write a code for the solar system, which at the beginning, I think many of you saw as intimidating, but when you look at the final result, this is actually something which one can be proud of having done. And I think it's fun. The two-body scattering is something which we didn't cover, but you will find it in the lecture notes, and that's an extension of this central force and two-body problems. We've been looking at variational calculus and Lagrangian formalism, and we've been looking at Lagrangian formalism with constraints. So the final project has actually, in the last exercise, it's about the pendulum, and we actually went through that during the lectures, and you already written a code for that in homework 7. In that case, you will actually have to implement the Lagrangian formalism with a constraint. That's the very last exercise in the final. Feel free to ask questions and stop me, right? So this is roughly what we have covered. And we have also looked at ways to solve these problems. And probably now you see also this kind of me insisting on this one problem, one code to solve all problems, to rule them all. We have essentially what we've done is we have set up a numerical solver where the only thing you need to do is actually to change the forces and find the acceleration. And then you can switch between 1, 2, and 3 dimensions and solve problems with many different types of forces. So when you analyze a problem, you find the forces, you have the acceleration, and that's what you would plug in any of these methods. And typically, if you have energy conserving forces, you would use Euler-Krohmann velocity Rayleigh. The Runge-Kutta family of methods is very much used when you're looking at oscillations and time evolutions of, let's say, the pendulum or harmonic oscillation, double pendulum, any of these problems, which don't conserve energy. And the reason why you use them is that you have a numerical approximation or mathematical truncation error, which scales like delta t to the power of 5 if you use Runge-Kutta to 4th order. And that means that when you simulate long enough, the error you make is small, even if you don't conserve energy. And also these methods are typically applied to systems where you dissipate energy, where you can have some kind of friction type so that the system is not an energy conserving system. But we are talking about the system because you typically make a system and then you have the environment. And sometimes the coupling to the environment is so complicated that you actually have to look at systems which don't conserve the energy. But if you were to describe the coupling to the environment properly, you may have a model where you conserve energy. And when you typically have so-called fundamental laws like the gravitational law or the gravitational force or the Coulomb force or forces like that, then energy is always conserved, but then you're often looking at isolated systems where you only have internal forces. And then we actually used to derive this Runge-Kutta family of methods. We looked at the methods for numerical integration in order to integrate up. So essentially, if you look at it, we've been looking at the variance of this program. So this would be a three-dimensional case. And you have to find the forces which depend then on the position typically. So this is in a case where you have a force which only depends on the spatial degrees of freedom. There's no velocity and no time dependence. You could have a time-dependent force, then you would have to change it here. You divide by mass, and then if you use the Euler-Kromer method, so this case is an example of the Euler method, or because then what you would have to do if you use Euler-Kromer, you would have to have a V of I plus 1 here. So this is actually not correct. This is actually the Euler forward method. So these are the kind of, if you now look back at what we have done, you could now, and this is something which we listed at the beginning of the semester, and in the beginning of the semester, this is something which we don't always think of. So with hindsight now, when you look back at what we have done, these are the kind of learning goals which we've been setting for this course. So take a look at them when you have some free time and see if you feel that these kind of learning goals have been achieved. And also, I got a reminder to remind you of this SIRS forms, because this year there's a small time window. I think they close them by the end of this week. I don't know why. So when you look at these forms, take a look at the learning outcomes and see if we have been able to achieve many of the goals which we have set out when we began the semester here. So I'm not going to read everything here, but you can take a look at these things. And then when it comes to competencies and skills, clearly to solve many of these problems, we have through different midterms and weekly exercises studied many systems numerically, from falling objects with and without friction, small oscillation, gravitational problems, and other central force problems, and the classical pendulum, which is something you will encounter in many of these studies in classical mechanics. And then these are the methods, the numerical methods, which we have studied throughout the semester and applied when solving the equations of motion. And then you could ask, why computations? So this is one of my hobby horses. And I believe that doing computations allows you to gain a deeper insight about physics problems. I think that if you look a little bit deeper, when you compute something, you have to ask yourself, what does it mean? Is this correct? Do I expect this kind of behavior? I have an energy conserving force and I don't conserve energy. What has gone wrong? This is a typical example of the way you would reason. You have an understanding of what can go wrong with the algorithms. We have looked at important algorithms for solving mechanics problems. Essentially, this is actually differential equations and some integration. And I hope also you see that we can use these algorithms to solve mathematical problems, which means that, like in our case, what we have done is essentially to take a continuous equation, and these continuous equations have analytical solutions in only some few cases. By discretizing them, we open up for the possibility to solve many more complicated problems, which means that by discretizing, we can now look at problems like the solar system, which would not have been possible by standard paper and pencil. You can actually solve the free body problem analytically, but that's only in specific limits. Whereas if you want to deal with many bodies, like we did for the solar system, you would have to revert to numerical exercises and numerical solutions. So to understand how these can be used to actually allow you to get a deeper insight about the physics, and I hope that when you solve the second midterm, you actually got this deeper insight about gravitational forces. Then this is something which gives a kind of strength of computations, because you would actually have one program which you use to solve many types of problems. So by scaling the equations, you saw that you could actually reuse basically the same program. Then you also make science reproducible. So by using GitHub and everything, it's easy for me to download things and check that things are running correctly. So we're actually making what we are doing reproducible. And I think, and this is actually, and perhaps you may not fully agree, or you may not see the full reach of it. I think this kind of algorithmic thinking is a way to gain deeper insights about scientific problems. And also the way you have been solving problems, like in the second midterm or the first midterm, is the way you typically solve scientific problems. So you would use all possible tools, whether these are symbolic ones with Mathematica, paper and pencil, and numerical analysis. So these are typically the tools which you end up using when you do science. And if you think of the solar system problem, I'd say just 15, 20 years ago, this would be something you would present to people when they're beyond their undergraduate studies. It would typically be a problem you would present for beginning graduate students. And for some people, this would even be parts of a graduate or a PhD or the beginning of a PhD. Whereas now we can actually solve this when you guys are in your second year of studies, which I think is allows us to explore physics at a very different level. Now, what I've taken out, however, when you introduce more numerical exercises, we put less emphasis on many of these paper and pencil exercises where you have to find a trick. I've never been too fond of that because that often takes away the attention from physics and you gaining a deeper insight about the laws of motion and physics. So I hope this kind of philosophy of mine is something which people have liked. We've taken away some topics like rotational problems because they can often be expressed better if you have had a course in linear algebra. So things like Coriolis forces and other examples where you move from an inertial frame to a rotational frame is something which we haven't focused on. But that's also because we spent more time on specific topics. So there are topics which I've taken out and which you will encounter if you take a more advanced course on classical mechanics, which we have a course which is, I think it's 480 and 880, which is the graduate course in classical mechanics. And that starts typically with the Lagrangian formalism and moves on with the Hamiltonian formalism and introduces rotations and many, many other things. And this is a course where you would have the full benefit if you've taken a course on linear algebra. And since only less than half of you have linear algebra, there are topics which I, by natural reasons, have taken out. So I hope you can forgive me for that. Yeah, you've seen this before. That's I believe in procrastination. And even if we have procrastinations, we do have a hard deadline. And that hard deadline is actually me having to punch in the grades. So that means that we will try to be a little bit more picky with the deadlines. And obviously, it's always been a great pleasure. Actually, I always think it sounds a little bit pathetic, but it's always sad when the semester ends because I get to know you guys and I had a great pleasure in reading midterms, your answers and everything. It's always a great pleasure to get to know you. And it feels a little bit sad when the semester is over, a little bit. I guess you don't share that kind of point of view. I mean, I was very happy when the semester was over. I think it's always a little sad. I will miss you guys. Okay, so what I wanted to say something about now is actually the final exercise, which we have a project. So I always struggle with making these kind of things. Sometimes they may perhaps end up being too easy, and other times they may end up being too difficult. But I hope I've been able to find a kind of balance. And since we've been spending so much time on the solar system, gravitational problems, etc., I thought we could go back to the beginning of the semester. And this is essentially something which is similar to what we did in the very beginning with a falling object. So you will see that in this case, one of the emphasis is actually you analyzing the problem, finding the forces, and then integrating up. So for the case when you go to 2 dimensions, you will not be able to find an analytical solution. So this is pretty close to what you had in the 3rd homework. Remember, the 3rd homework was the falling object. And in the 4th one, you had the possibility to let the object bounce up and down again. So it means that from a programming point of view, you can actually reuse what you did in the 3rd homework, basically everything there. Except that now the problem changes a little bit with the forces. So you have to identify the forces. And when you've identified the forces, you can actually reuse what you've done. So some of this can be solved analytically, whereas some of the other parts have to be solved numerically, especially the case when you go to 2 dimensions. So you will see that rather quickly. So that's there are many small exercises here, as you probably have seen. It should be also in GitHub now. I put it on D2L and I sent it as an email to all of you so you could take a look at it before you came here if you had time to. And they're just a set of small questions, and then finally there's the numerical part where you can actually reuse the codes from homework number 3. And there are just some small minor modifications where we adjust the velocity, the wind velocity according to height, etc., etc. And then we have the next one, which is, and you can see you're being here reminded of my fantastic drawing skills, which have suffered throughout the whole semester. But hopefully this looks like a pendulum, or just imagine it is a pendulum. And what you have to do then, in this case, is actually look back at the homework number 7, where you actually had a code for the type of harmonic oscillations and the pendulum. And what you're going to do then is simply to first solve the differential equation. So you're not going to derive these equations. As I said, you don't need to show this. And then we are going to look at the small angle case, where you can approximate sine of phi with just phi. And then when you do it numerically, you can then compare that with the small oscillation case, where you have an analytical solution and the numerical solution here. And then it follows, when you move down here, the final part is actually the one which deals with the Lagrangian formalism. So you need to set up the kinetic energy, and you need to set up the constraint here. And then you will derive an equation for lambda here, and you need to interpret this parameter lambda, whatever it means. So the last exercise 2F here is actually you using the Lagrangian formalism with a constraint. The parts before here are not that different from homework number 7. So much of what you've done in these homeworks are things which you can reuse in the solution of the final one. So I hope I've been able to strike this balance between the amount of time which we should use on it and what you've done throughout the semester, and that it's not too time consuming. It's always difficult to strike the right balance. It takes me a long time to make these exercises, and I'm always in doubt whether I've been able to strike the right balance. I think the one I gave last year was a little bit too complicated. It took more time. And I think this one is on the lighter side. If you think it's too light, we can always add more exercises. Yeah, I see somebody agrees with that. Anyway, I'm going to stop here, and then we are going to discuss the final one. Feel free to ask questions if you wish to hang around after our time here. I'm going to stop the recording. You can re-watch the recording. And then, yeah, you have Friday. You can, if you have time, I will be here on Friday from 3 to 5, and same next Monday and Wednesday. And then we can see if we need more time next Friday as well. Okay, guys, it's been a great pleasure to meet you. And never hesitate to ask questions. Never, never. Okay? Promise? Okay, thanks. Thanks so much, Jake.